Alright, let's try again. How are we looking? How's the audio check? Awesome. Sweet. Alright. I don't know if it's gonna work, but let's give it a go, hey? So I put the PDF on Edmodo as well, which is essentially this document here. And I guess we just start off with a kind of quick revision of inverse trig functions. And I've given you like the basic graphs here of, sine, cos, tan, and then the inverses as well. And I think the tricky thing to remember is that with inverse trig functions, you remember that you actually have to sort of define a domain, and then we take the inverse of that. Because sine, cos, and tan are periodic, there won't be inverse functions unless you restrict the domain in some sense. So that's what we do here. And in some sense, it's kind of arbitrary. Like, why do we choose -1 to 1? Negative pi on 2 to pi on 2 for the original function. And I guess that's just the way they defined it. But it allows us to create these inverse functions, which we also refer to as arc, right? So we've got arc sine of x, that's the inverse from -1 to 1 and negative pi on 2 to pi on 2. And you can see the respective ones there. I think the interesting to note is with inverse tan, right? Because the range of the original function tan of x goes from -infinity to infinity. Remember, when you take the inverse, we're going to swap the domain and ranges. And so when we're swapping the domain and ranges with our inverse tan function, what's going to happen is that now the domain will go from -infinity to infinity, right? So that's all well and good. Let's have a look at inverse sine, right? So inverse sine, some things to note about when we draw it. So if I just quickly go back up to sine here, you'll notice that these endpoints here that we've chosen, they're actually horizontal, right? So if they're horizontal, if we taking the inverse, remember, you can think about it in two ways, either swapping the x and y values or reflecting the line y equals to x. So when you do that, you'll notice that these endpoints over here, they actually become vertical now, right? So that actually needs to be reflected in your drawing as well. So just make a note of that. So if we go back down here, we remember that we're swapping the domain and ranges there. So this time our domain is going to be from -1 to 1, and our range is going to be from negative pi on 2 to pi on 2. Okay, and then when I'm drawing that, I also have to reflect that in this construction. And if you're a bit unsure of how to start, I always kind of split up the construction. So I'll say, I know that these endpoints have to be vertical, and when I make this construction, let's try that again. There we go, to the origin, and then just point up like that. So I guess there's your endpoints like that. Sweet. And there's our inverse sine function, right? Now, I guess the question is, how do we make changes to that? And I want to start using this language of dilations and translations, because that way, when we get to the assignment in that chapter, then that's going to be something that's more familiar. So the first thing we can do is, let's look at a vertical dilation. Right, so we know that's when we put a number in front, or a coefficient in front of the whole trig function. And I guess we usually refer to that as the amplitude for our normal trig functions. With the inverse trig functions, we can expect something similar, but we just want to be careful about how we actually construct it. I think the best way to do it is to take your trig function. So we've got y is equal to 3 sine inverse of x, right? And you want to remove any kind of coefficients or any differences like that. So in this case, I'm going to divide both sides by 3. okay? And I want you to think about like what's the normal range for our inverse trig functions. Just go back up. So our normal range is I'm going from negative pi on 2 to pi on 2, right? So we take whatever's on this left-hand side over here, because I know that this has to be between negative pi on 2 and pi on 2. Then my life stream stop. Yeah. We're still good. Why did this thing die? Wait, I'm still going. Wait, it's still working. Yeah, okay. I don't know why it told me that. Yeah, anyway. Let's go back. Okay. Poggers. I don't know what that is. It's working. Alright, cool. Okay. Just my things being dodged. Alright, cool. So we take this guy and we're like, alright, I need this to be between negative pi on 2 and pi on 2, right? And so let's go ahead and do that. We'll go, this guy here needs to be between negative pi on 2 and pi on 2. So I'll put y on 3 inside that kind of restriction. And I'm pretty sure we take the endpoints. Let me just double check. Yeah, we do. Okay. Just do a quick check. Yeah, nice. And then, so then I'm saying, okay, for my range, then I want to get y as the subject. So we just want y by itself in that inequality. So we'll multiply both sides by 3, and we'll get negative 3 pi on 2 and 3 pi on 2. Alright? And then we can construct that because it's the only transformation that we have on this. So let's go ahead and do that. Probably did that curve a bit too intense. Let's go and do that again, hey, just for good measure. So what happens when you try and do it in one go? It just kind of doesn't work out. So the only thing you're changing is the range here. And so we just change that guy like so. The domain remains the same there, so it's negative 1 to 1. So you can call that a vertical dilation with a scale factor of 3. Okay. Yeah, I'm bumping the views, just putting myself in there. Should put some spoof accounts. Yep, being recorded. I don't know if, I don't know, because I'm guessing there's like a lot of just downtime. So maybe I have to cut it a bit. Yeah, but it's a small math class. Gonna have to do a lot of push-ups, I reckon. Yeah. Okay. So maybe let me know what you reckon will happen with these guys here. Oh, I kind of gave it away. Well, I haven't actually. So when we put this value of x inside here, we know there's going to be some sort of like horizontal change. So in this one, it's a horizontal dilation. So yeah, let me know what you reckon. What kind of scale factor are we going to see with this one over here? Don't know how live this actually is. Oh, that was really, this must be like pretty quick. All right, cool. So yeah, the domain will change. And I guess the question is by how much? If we go back to like the natural language of this domain and dilation, what we recognize is we're saying, okay, well, let's use the same idea, right? 2x is what's inside the brackets at the moment, and the restriction on what's inside the brackets, just go back to the original ones, right? The original one says that the domain is from negative 1 to 1, yeah? So negative 1, and yeah, that's exactly right, Carl. We've got a scale factor of half. Why exactly do we have that? Because if I take this guy and I'm saying, okay, that needs to be between negative 1 and 1, what does x need to be as a restriction, well, then we can get x as a subject and using that same idea, and we can get negative half. Wow, that was not great. Let's try that again. Negative half between x and positive half. Alright, cool. And so that's why we'll say that it's a scale factor of half, because now this time what's happened to the domain? The domain has actually halved, yeah. Maybe we can have a go at drawing that. So yeah, there's like the construction, and hopefully it's like pretty clear why that's happening, right? So let's go, there's the original, and like if we had a coefficient of 3, cool. Can you see, I guess, yeah, now, like the black one over here, that's by a scale factor of 1 over 3, right? Just see if we can see that a bit more clear. There we go. Now I like the 0.5 step there. Cool. No, unfortunately. It's just some random HP one. Cool. Oh, good. Let's get back to the document. And we can construct that one too. So this guy, we know that it's a scale factor of half, right? So just drawing this one out, then you go back to pen mode. It's not the best, so we'll roll with it. So keeping the range the same, but then the domain has been halved, so we go from negative half to positive half. Cool. And oh, there's 2 more. Do you guys want to have a go at that, or do you want me to just do them? Yeah, that's not happening, mate. Should I just do these ones? Oh, okay. I reckon you can do them though. Like, so I think here's the basic idea with like any of these transformations. Like anytime you're graphing them, right? The idea is that we can always apply the same principles. So if we have something like this, I'm adding a, yeah, that's right, Angus. It shifts it up high, and so we'll mark that in. I guess the thing you have to be careful though with this one is that, again, like always go back to the original if you're not sure. Like with the original one, it goes from negative pi and 2 to pi and 2. So you just have to think about, okay, like where is this actually going to sit in the axis now, right? Or in the coordinate plane, because, you know, sometimes if you shift it up less than negative pi and 2 units, then, sorry, Dr. Orange, anonymous. If we shift it up pi units, we want to think, okay, where is it actually going to sit? And you think about, you're over here, right? So I'm on negative pi and 2. I'm shifting up pi units. You're actually going to be starting over here now, right? Because, you know, this total distance here is pi. So it's just got to be, that's something you want to be a bit careful out with these ones here. Because we're working with radians, it's a little bit more unfamiliar. And if we're shifting with numbers and things like that, like +1, that's not immediately obvious where that's going to sit. So just be careful. So we know now if I'm shifting up pi units, then my range is now going to be from pi on 2 to 3 pi on 2. Right? And so marking that in, that's the bottom section. Here's the top. It's pi over here. And then, oh, that wasn't quite vertical enough for me. Oh. Yeah. didn't draw. What's going on? There we go. Right, nice. Is arcsine plus pi equal to arcsine cos minus x? 2. Let's have a look. I'm actually not too sure. We'll find out together. So inverse x plus pi on 2. Okay, that's what that looks like. And we've got arc. Oh, it's not an arc. It's cos. I do have it if you. I can send an emoji if you need it. Oh wow, it is. How'd you work that out? That's pretty cool. What's the normal look like? Okay, so you're reflecting it in the y-axis, and then this one you're shifting up by pi units. Yeah, that's pretty awesome. And I guess similarly, what if we do this? What if we do like pi on 2 minus x? Nah, that didn't work. Minus x and then shift it down pi on 2 units. I guess that would work too. That's kind of not as nice though. I like the one better. That's pretty cool. That's probably actually an identity that we might need to use. So yeah, good observation. All right, last one before we wrap up. I do actually have some others if you do have some other questions if you guys want to do them. But let's just finish up with this one for the inverse trig ones anyway. So horizontal translations, right? Same idea. I'm thinking, okay, what's this gonna do? And I always say there's 2 ways of thinking about this. If you have a positive and negative, you can memorize what these translations do, right? So we can say, let's go back to this one. And if I'm saying, all right, let's add half and see what happens. Okay, oh, we've shifted it in some way. I'll keep the original one there so it's really obvious what's happening. Okay, so the blue ones are original, and okay, if I add 0.5, it looks like I'm shifting to the left. If I subtract, then let's just confirm. Yep, we're shifting to the right there. It's probably not helpful, it's the same color. Make a different one. Cool. So I guess, like, what's the intuition there? What? Actually? The intuition is that we have to make sure that, okay, where is this like starting? Because usually we start at x equals to 0, right? And so I always think about, okay, what value of x do I need to make the brackets 0? Well, for this red one here, when x is 0.5, that's when the brackets will contain 0. And so that's your new sort of starting point, so to speak. Yeah, so here's sort of what I've been kind of reflecting on lately. I don't know whether it's better to think about shifting or using the inequality. I think it would depend on the question. So if I go back to the questions, right, like with this one here, I think it's very easy to just think about I'm shifting up pi units. So you just add that to the range, right? Like you don't have to set up the inequality and stuff like that. So that, like, I think you don't really need to do anything with that. I think it's a bit more difficult with the dilations and things like that. I prefer to use inequality because it's a bit more algebraic, and so I find the approach easier. But I'm sure you can also just think about it as, like, if it's a scale factor of 3, you're just multiplying the range by 3. So I think it's more of a personal preference thing. Okay, shifting works. Yes, I believe so. I can't think of any differences at the moment. So yeah, let's go with that for now. Cool. And I think that's going to wrap us up, eh? So what's this going to be? This is a horizontal. I think it is important to be aware of, like, I think they can craft questions now that ask you, okay, yeah, like which way is it translating, or like how exactly is it dilating? Like the scale factor thing is something sort of new in the course, so we have to be familiar with that language. Yeah, we could do tan, hey? Let's just let's do this last one. So what was it? X minus 2. Let's just cheat and be like, what does that look like? Okay, so we can say, okay, negative is shifting to the right, positive is shifting to the left. Right, so negative shift left and positive shift right. Man, try that again. Okay, and so I guess what are we doing here? We are shifting. We're shifting horizontal of 2 units to the left. Okay, and go ahead and mark that in. Oh, the wide. Wait, did I say left? Why did I say left? Negative. Yep, no, definitely messed that up. Let's go ahead and do that. Fix that up again. Oh, okay, I can only undo so much. Try that again. Thanks, Callum. We're shifting negative, we're shifting to the right. Cool. Yep, I'm lagging. So here's 2, and I guess we'll look something like this. That's not bad. 1, it's a negative 1, and what's this guy going to be? 1 and 3, right? Because our usual, let's have a double check. So 1, like 1 unit on either side, so it should look like that. How do we go? Yeah, nice, like that. Pioneer. Yeah, I don't know that. I know a lot of teachers actually done it before. Cool. All right, that's first live stream. I'm actually using my iPad, and it's got a stylus, but I think it doesn't work very well when you try and do it. I had to mirror it to my computer. Oh man, it's so complicated. Cool. All right. How do we go? Do we want to try another one or? Yeah, who is how to basic now? Alright. I don't know. Maybe you guys just have the rest of the day off and I just upload the PDFs. Whatever you guys want to do. You guys let me know. This is fun day. So that lets you do 4.01 question 10. So that actually wasn't any of the work that we, yeah, 10 is pretty much the same stuff. And let's just have a look. So there's inverse tan of x, and then like the important thing to know is like where the asymptotes are. You've got negative pi and 2 and pi and 2 as the asymptotes, and it's like you can do the shifts and all that. Wait, what? Oh, I need y equals 2. No, I need x actually. That's what I need. There we go. Yeah, you can do your shifts up. You can do your shifts down. Yeah, dilations are kind of like weird, right? Because so we're actually changing the asymptote here is the important thing to know. So if you do 2 inverse tan of x, like the asymptote now becomes pi negative pi. Whereas if you do like tan inverse of 2x, like, okay, what's actually going on here, right? Because that's meant to be like a horizontal dilation by a scale factor of half. So like you can think about all the values being halved, so to speak. So like where you would usually get pi on 4 at x equals to 1, now you're getting pi on 4 at x is equal to 0.5. So that's like how you actually think about the dilation, like the kind of coordinates of where you are, right? Yeah, and you can still use like the inequality tricks and stuff like that. I think that's, yeah, that's why I kind of like the inequality approach, because yeah, it works well for that. Yeah, cool. And I've also got the solving trig equations, but you can kind of do them yourselves. Wait, what? Okay, maybe I'll stop this one, and then I'll upload the PDF and have a look at it, and then we can always come back if we want to do that. How's that? How do you guys feel about that? Maybe I'll like give you the trig equations one just to have a look at, and then I don't know. What do you guys reckon? Right, let's do that. How do I stop this? End stream.